Imagine this! You're an engineer hired to build all the streets in a subdivision. There are 8 houses, and you are given a blueprint of all the possible streets that can be built. Moreover, the construction cost of each street is different. Here is your blueprint, along with the respective construction cost of each possible road. Now, what would be the cheapest way to build a road system such that there is a route between any 2 houses? Well, to answer this question, we need to make use of a concept in graph theory known as minimal spanning trees. But before we get into that, let's define a few terms. First of all, what is a graph? A graph is a structure that consists of vertices that are connected by edges. The graph shown is an example of a simple graph such that it contains a non-empty set of vertices and a set of undirected edges. It is also a connected graph wherein there is a path between every distinct pair of vertices. If we add weights to the edges, our graph becomes a weighted graph. This graph also contains circuits like ABDGF, BDGE, and BCHGE. Moving on, a tree is a connected, undirected graph with no simple circuits. Graph 1 is an example of a tree because it is connected, undirected, and has no circuits. Graph 2 is not a tree because it contains a circuit, specifically FIJH. And graph 3 is not a tree because it is not connected. Now the word spanning means to cover. Therefore, we can define a spanning tree as a tree that is a subgraph of a graph that contains every vertex of the said graph. Let's explain this further with an example. Here we have graph A, whose total edge weight by adding all the weights of each edge is 15. We can get one spanning tree by connecting A to B, then B to D, then D to E, and E to C. This tree has a total edge weight of 9. We can get another spanning tree by connecting D to B, then B to A, then A to C, then C to E. This tree has a total edge weight of 11. Graph A actually has 9 other spanning trees. Can you list down these trees along with their respective total edge weights? Pause the video so you can answer. Here are all 11 spanning trees of graph A. If we compare all their weights, we see that spanning tree 1, 5, 6, and 9 have the smallest total edge weight, which is 9. These are known as the minimal spanning trees of graph A. From this example, we can define a minimal spanning tree, or MST, to be a spanning tree with the smallest possible total edge weight of a graph. But listing all possible spanning trees of a graph to find its MST seems pretty tedious, especially when we're dealing with graphs with a lot of edges and vertices. Luckily for us, we can make use of greedy algorithms, which make the optimal choice at each step to find the best solution to a problem. In this video, we will be tackling 2 algorithms that can be used to find the MST of a graph. The first algorithm is Kruskal's algorithm, which was developed by Joseph Kruskal. It focuses on locating all shortest edges in a graph in order to form a tree. This algorithm is good for manual calculations, but is hard to program into computers because it requires regularly checking for circuits. The steps are as follows. Choose the shortest edge, choose the shortest remaining edge that does not complete a circuit, then repeat step 2 until n-1 edges, wherein n is the number of vertices, are chosen all together. Now let's try using this algorithm to solve our first problem, which is to build the road system of the subdivision. Let's take a look at our blueprint. We can consider the houses as our vertices, the roads as our edges, and the construction cost of each road to be the weights of these edges. Using Kruskal's algorithm, first we choose the shortest edge. The shortest edge in our graph is 30, and there are 2 possible edges to choose from. We can start with any of the 2. Let's choose edge BD. Now, we choose the shortest remaining edge that does not complete a circuit, which would be edge GE. Let's keep doing so until we have selected 7 edges all in all. So far, we have selected 2. The next shortest edge is 35. We can choose edge BC and then edge FG. Now, we have selected 4 edges altogether. The next shortest edge is 40. We can choose edge FD and edge AB. We can't choose edge BG because it will complete the circuit FDBG. The same goes for edge EC because it will complete the circuit FDBCEG. Now we have chosen 6 edges. For our last edge, the next shortest edge is 45. Therefore, we can choose edge GH to complete our MST. Now we have found the cheapest way, costing 255,000 pesos, to build a road system for our subdivision. Another algorithm we can use to find MSTs is Prim's algorithm, which was developed by Robert Prim. Unlike Kruskal's algorithm that focuses on finding the shortest edges, Prim's algorithm focuses on gradually adding vertices that are not connected to the tree being constructed. It's easy to understand and programmable through matrix form, but tends to be complex when edges have the same weights. The algorithm starts a tree by choosing any vertex at random. Then, we add the shortest edge which joins a vertex on the tree to one not on the tree. This is repeated until all vertices are part of the tree. Let's try making another road plan for our subdivision, this time using Prim's algorithm. First, we start the tree by choosing any vertex, say vertex G. All possible edges that connect G to another vertex are highlighted in orange. The shortest edge among the highlighted edges would be edge GE with the weight of 30. Therefore, we add vertex E to our tree. Now we repeat the process until all vertices are added to the tree. All edges that connect vertices not on the tree to vertices on the tree are highlighted once again. The cheapest edge we can add would be edge FG, which adds vertex F to our tree. If we highlight all possible edges again, we can see that there are 3 possible vertices to add, namely vertex D, D, and C. In this case, we can choose any of the 3. Let's connect vertex C to our tree. Highlighting all possible edges again, vertex B can be added to the 3 through edge BC, which weighs 35. Among the possible choices, the best choice to add is vertex D to the graph through edge DB. Now the optimal choice among the highlighted edges would be AB with weight 40. And finally, we add vertex H to the tree by choosing either edge GH or CH. Let's choose edge CH. And voila! We now have another MST for our graph. With this MST, we have a different road plan which also costs 255,000 pesos to build. With your skills, you were able to construct a road network in the subdivision which saves a lot of money but still satisfies all the residents. Congratulations and a job well done indeed! Here's something to ponder on. Can Kruskal's and Prim's algorithm be used to find the MST of a graph with negative edge weights? Let us know in the comment section below. Now, road networks are not the only application of minimal spanning trees. They can be used to solve approximation algorithms such as the traveling salesman problem. Take note though that MST problems are different from shortest path problems. MSTs are concerned with finding the cheapest ways to connect all possible vertices in a graph, while shortest paths are concerned with finding the cheapest way to get from point A to point B. Another application of MSTs would be cluster analysis. This can be used in the field of biology in clustering gene expression data. Lastly, MSTs can also be used in designing networks, for example in telecommunication and electrical grids. Today we tackled the basics of graph theory and defined minimal spanning trees. We talked about the different 3D algorithms that can be used to find MSTs, like Kruskal's algorithm and Prim's algorithm. And finally, we listed the applications of MSTs in the modern world, like approximation algorithms, cluster analysis, and network design. I hope you learned a lot today. This is Genellie Erap, and don't forget to like and subscribe.